Welcome back to this course, Advanced Memory Hierarchy Design. In this final lesson in this course, I will give an example of hardware prefetching, briefly discuss stream buffers and the speed up due to hardware prefetching, and I will give a brief summary of all the cache optimization techniques discussed in this module. I now give an example of the contents of the RPT after a certain time. Here is matrix multiplication again, as we have seen several times before. But now I use single precision floating point instead of doubles. Suppose now that the matrix A starts at word address 10,000, B at word address 20,000, and C at word address 30,000. Notice that each matrix has 10,000 elements. Then part of the content of the reference prediction table after iteration I equals 10, J equals 20, and K equals 30 is shown in this table. If there are no conflicts in the RPT, the load of BIK, the load of CKJ, and the load of and the load of AIJ will all be in the RPT. Let's consider the load of BIK first. The word address of B1030, which is the element access in this iteration, is 21,030 decimal. B starts at word address 20,000. Row 10 starts at address 20,000 plus 10 times 100, which equals 21,000. And then element 30 of row 10 is located at word address 21,030. Furthermore, the stride is one word since B is accessed along the rows. Notice that I use words for the addresses as well as the stride. To obtain the byte address and the stride in bytes, they need to be multiplied by 4. In the same way, the address of C3020 can be calculated as 33,020. C is accessed along the columns in the inner loop. However, so the stride of this load is 100 words. And finally, the address of A1020 is 11,020. AIJ is invariant with respect to the inner loop, and therefore the stride is 0. For this load, the hardware prefetcher will not issue a prefetch. To prevent that prefetches pollute the cache, meaning that they replace data that is still needed in the future, blocks can also be prefetched in so-called stream buffers that operate in a FIFO fashion. Then, if the CPU performs a memory access instruction, both the cache and the head of the stream buffer are checked to see if the requested block is there. If we have a cache miss but a stream buffer hit, then we bring the line to the cache and initiate the next prefetch to sequentially fill the stream buffer. The beauty of this scheme is that if we make the stream buffer large enough to hide the memory latency, the prefetches can be initiated exactly on time. If both the cache and stream buffer miss, then we flush the stream buffer because apparently data is not accessed in a sequential or strided fashion. A stream buffer works well for instruction caches, but less so for data caches. Different loads typically access different arrays, and each array basically requires a separate stream buffer. The Pentium 4 had a hardware prefetcher that monitored data access patterns and prefetched data automatically into the L2 cache. This hardware prefetcher could be turned on or off since not all applications benefit from hardware prefetching. This figure shows the speedup achieved by the hardware prefetcher for 2 of the spec int 2K benchmarks and 9 of the 14 spec floating point 2K benchmarks. Only the benchmark that benefited the most from prefetching are included. The missing 15 spec 2K benchmarks were accelerated by less than 50%. As expected, prefetching is beneficial mostly for scientific floating point programs, since such programs typically process large matrices. The maximum speedup that is achieved is 1.97 for the earthquake simulation benchmark, which is impressive, but such large speedups are very rare. Usually the speedup due to prefetching is less than 30%. On this and the next slide, I summarize all cache optimization techniques that I have discussed in this module and the impact of each technique on the hit time, the miss rate, the miss penalty, the cache bandwidth and the power consumption, as well as the hardware cost or complexity of the technique. Plus means the technique has a positive impact on that criterion. Minus means it has a negative impact, and the hardware complexity is rated from 0 to 3, meaning 0 meaning very low complexity and 3 meaning very challenging. I will not discuss them all, but you should be able to make a case why a certain technique has a negative or positive impact on different criteria. To give an example, higher associativity typically has a negative impact on hit time, since direct map caches are faster than set associative caches. It has a positive impact on the miss rates, since there will be fewer conflict misses. It doesn't affect the miss penalty or the cache bandwidth, and furthermore, higher associativity usually reduces the power consumption. Well, it depends. A hit in a direct map cache consumes less power than a hit in a set associative cache, but a main memory access dissipates much more power. Therefore, reducing the miss rate is often more important than reducing the power consumption of a cache hit. Here's the rest of the table, and finally some exercises that ask you to explain what prefetching is and why the data loaded by a prefetch instruction is often not directly placed in cache. This completes this lesson and this course on advanced memory hierarchy design. In the future, I intend to add some lessons on main memory, DRAM technology, and on scratchpad memories, which are fast memories that, unlike caches, are software controlled and are often employed in embedded systems. So stay tuned. In the next course, I will discuss multi-core systems. Hope to see you back.